All right, so in this video, we're looking at a review of systems of linear equations. So there are different ways we can visualize solutions for systems of linear equations. So we have three options. We could have a system that has one solution. So we have two lines that cross, and right here, this is the point, right? The ordered pair that makes both of the equations true, right? It's the one place where they cross. Over here in the second one, we have no solutions. There's no points on this line here that will also show up on this line, right? So here, since we have no solutions, that really happens because our lines present as parallel, and parallel lines never intersect. Okay, our last option is we could have infinitely many solutions. When we graph a linear equation, it might end up that the second equation we graph is identical to the first. They're the same line, but in different formats. So we have any point that's on one line is also on the other line, which gives us infinitely many solutions. So to give you just examples of what this could look like, let me slide this up. Here, if the lines intersect, I could have y equals, let's say, 2x plus 7. And I could have a second equation, y equals maybe negative 1/3 x plus 1. Right? Those two lines, they would cross at some point in one position. So there's one solution they would share in common. Here, if the lines are parallel, never going to cross, that means that they'd have to have the same slope. So that could look like y equals 2x plus 3, right? The slope is 2, the y-intercept is at 0, 3. And then another one could be y equals 2x minus 11. So same slope of 2, different y-intercept. So these lines, they would never cross because they have the exact same slope of 2. Okay, if the lines are the same, here infinitely many solutions, let's say that I write the first line as y equals, let's say 1/2 x minus 4. Okay, let's say that that's my first equation. Imagine that I put a multiplier on each of these terms. Let's say that I double each of these terms. I multiply by 2. That would be 2y equals x minus 8. So I've multiplied each of these by 2. This is my new equation, but it ends up actually being the same equation as the first. All that's changed is every term here got doubled to create this equation here. And if I was going to graph each of these equations, they're the exact same line. All right, next is a review of the methods of how we solve systems. So first I'm looking at graphing. So I'm giving you two equations. I am giving them to you in a different format. So the first one is in standard form. So this one I would probably graph the intercepts. So if I'm looking for the x-intercept first, that's when y is 0. So if I look at that first equation, if I put in a 0 for y, that clears this part up. I'm using that cover-up method, and I'm really solving 5x equals 15. So when I divide each side by 5, I get that x equals 3. So x equals 3 when y is 0, so my x-intercept is at 3, 0. So I plot that point right here. Okay, the y-intercept is when x equals 0. So if I plug in a 0 for x right here, I can cover that up because that whole term clears to 0. And I'm really then solving negative 3y equals 15, dividing away that negative 3, getting that y equals negative 5. Of course, that's when x is 0. So as a point, that's 0, negative 5. So my point is right here. So what I can see then, since I have those 2 points, let me slide that up, is that my slope is really going up 5 and right 3. So I could give myself a few more points. Go up 5, right 3. Go up 5, right 3. And do the same thing here. go down 5 and right or left 3. There we go, opposite direction. There we go. So there is my first line, right? I'm just graphing it in standard form using the x and y intercepts. Okay, and then from there I know what my slope is. Okay, the second line here, I can see that that's in slope-intercept form. That's just y equals mx plus b. So my y-intercept, the b, is at 0, 3, so right here. And my slope is 1/3, that's the m. So I'm going up 1 and right 3, up 1 and right 3, up 1 and right 3. Right, and I can see my line, I can see where they cross, I can see that they have 1 point in common. And that solution right there is at 6, 5. So that is my solution to this system. If I plugged that 6, 5 back in, so 5 times 6 minus 3 times 5, right? 30 minus 15 gets me back to 15. If I plug in here, let's see, the x is 6, so 1/3 of 6 is 2. 2 plus 3 equals that y value of 5. So I can plug it back in and verify that both of my equations are true. Okay, another method that we use is substitution. So I'm going to solve the same system using a different method. So substitution. So when it's substitution, that means that it's easy to isolate one of the two variables, either x or y. And I can see that right here, that second equation already has the y value isolated. So I can take this part right here, that 1/3 of x plus 3, and I can plug it in for the y in that top equation. So now I have 5x minus 3 times 1/3 of x plus 3 is equal to 15. So the whole point of doing that is to create a one variable equation. Now I want to solve for x. So I distribute that -3. So 5x minus -3 times 1/3 is just 1. So minus 1x, right? We usually just write that as x. -3 times +3 is -9. And then equals 15. Okay, so now I'm just cleaning it up. So I have 4x minus 9 equals 15. I'm going to add the 9 to the other side. So 4x is equal to 24. Divide each side by 4. And we get that x is 6. So we solve for the x value. Now we need to plug in to get the y value. And I can plug into either equation, whichever one's easiest. I'd say that second one looks easiest, but it really doesn't matter. So y equals 1/3 of 6 plus 3. 1/3 of 6 is 2, plus 3 is going to get us to 5. Right, so y equals 5. We're verifying that we get the same ordered pair as our solution, which is 6, 5. Right, it's the one point that makes both of the equations true. Okay, last method that we use is elimination. So over here, I have my two equations, and I want them to be stacked in the same way. I want to see my x's together, my y's together, and then my constant on the other side. So I'm going to start by reorganizing that second equation. I'm going to subtract that 1/3 of x to the other side. Okay, so right now I have 5x minus 3y equals 15 on top. And on bottom, I have -1/3 of x plus y equals 3. Okay, so they're stacked with the x's, the y's, the constant. Now I need to create opposites in either x or y. So here I might think, well, if I multiply everything on bottom by 3, it's going to do two things. It's going to clear this fraction here, and it's going to create a positive 3y right here, which will make these two terms opposites. So that's what I'm going to do. I'm going to multiply everything on the bottom by 3. What I do to one, I do to all of them. So now if I rewrite that first equation, I have 5x minus 3y equals 15. And on bottom, I have negative x plus 3y equals 9. All right, so now I have opposites in either x or y. In this case, the y's are opposites. So now when I add down, I have 4x, right there's 0, equals 24. Divide that 4 away, and we're back to x being 6. Okay, and then plug back in to get the y value, right? We already did that in this equation, so we know that y ends up being 5 when x is 6. So again, same solution, different strategy, 6, 5. So those are the 3 methods for solving linear equations: graphing, substitution, elimination. Okay, lastly, I'm going to show you the 2 special cases. So here I'm saying let's graph each system and then solve using one of the 2 methods. So let's say here I look at that very first one. I see that that's in slope-intercept form. So my y-intercept is at 0, 1. So I start there. And I build off of that with a slope of 1/4. So I go up 1 and right 4, up 1 and right 4. Do the same thing in the opposite direction. So down 1 and left 4. I'll give myself one more point there. So there's my first equation. Easy. Slope-intercept form. Okay, the second one here looks easy to graph in standard form. So here, if I look for my x-intercept, again, that's when y is 0. So if I plug in a 0 for y, and this whole part cancels away, it's easy to see that x is -4, right? X is -4 when y is 0. So the x-intercept is at -4, 0. Ooh, I see it's in the same spot right there. Okay, if I go after the y-intercept, that's when x is 0. So if I plug in a 0 here, cover that up, then I'm really solving -4y equals -4. And when I divide each side by that -4, I get that y is 1. So that would be 0, 1. When x is 0, y is 1. Ooh, same point right here. So I see 2 points on the same line, right? If I take my ruler and I cross through, I see that it is the same exact line. So same line, which means that we have infinite solutions, right? Infinitely many solutions. Okay, so I know that graphically, but often we solve using a different method, right? Sometimes we solve using substitution or elimination. So let's imagine that we were solving this using substitution. And I'm going to say substitution because I see that the y is already isolated. So here, let's say that we take this part and we plug in here for the y, right? I'm just going to show you what it looks like algebraically. So if I plug in, now I have x minus 4 times 1/4 of x plus 1, right, closing my parentheses, equals -4. Okay, so if I didn't know graphically that it's the same line and I'm trying to solve this using substitution or elimination, let's see what happens to those x values. So here I distribute that -4. So x here, a -4 times 1/4 is -1, so -1x, and then -4 times 1 is -4. Okay, equals -4 on the other side. X minus x zeroes out, so we're left with this -4 equals -4 equation, which is absolutely true Negative 4 does equal negative 4, but I'm not solving for x or for y, right? The x's and the y's cleared out. So the fact that I'm seeing a true statement here, that signals to me another way algebraically that it is the same line, and we have infinite solutions. Okay, the last variation here. Okay, so here if I was to graph each of these, let's say I start with the first one. So here I might think, well, let's solve with our intercepts. I'll show it with fewer steps this time. So the x-intercept again is when y is 0. So if I plug in a 0 here, cover that up, I'm really solving for 2x equals negative 2. So when I divide each side by 2, I get negative 1 for x. So x would be negative 1. So negative 1, 0. Okay, y-intercept, right? X equals 0. So if I plug in a 0 here for x, cover that up, solving for negative y equals negative 2, divide each side by negative 1, we get that y is 2. So here as a location, that would be 0, 2 for the first one. So negative 1, 0, 0, 2. Let me give myself a few more points using that same slope of 2. All right, so there's my first line. Okay, my second one here. So then if I'm looking at this one, so my x-intercept, right, again, y is 0. So if I plug in a 0 here, cover that up, I'm solving for x. Okay, so 4x equals 4, divide by 4, I get 1. So I would get x equals 1. So 1, 0 would be my x-intercept, so right here. Okay, my y-intercept, x equals 0. So here if I plug in 0 for x, solve for y, and I'm dividing by negative 2, I get that y is negative 2. So as a point, that's 0, negative 2 for the y-intercept. So right there. Okay, and if I give myself a few more points, right, I can see that it has the same slope of 2, up to right 1. And since we have that same slope, right, these lines are parallel, right, parallel lines. So there is no solution. Right? There's no way that they are going to cross. There are no points that they're going to share in common. So again, algebraically, if I'm trying to show you what that looks like, I probably use elimination here. Let me rewrite the two equations. Okay, elimination, I want opposites in x or y. Let's say that I want opposites in x. Then I want the x's to be 4x and negative 4x. So I'm going to multiply everything on top by negative 2, making sure I distribute. So now I have negative 4x plus 2y equals 4. And then on the bottom, I still have 4x minus 2y equals 4. So when I add down, I see that the x's are opposites, the y's are also opposites, so this left side clears to 0. And on the right side, when I add down, I get 8. So here I get this statement here where that is a false statement, right? The x's and y's cleared away, but I get a false statement, and that tells me that there is no solution. All right, so when I look at things algebraically, just to recap, if I get something true like this, x and y wipe away, that's infinite solutions. And here, if I get a false statement, that is no solution. All right, have a good day.